All right, here we go. Unit 3, Lesson 5. I'm going to work with some exponential and logarithmic models. Just kind of wanted to show you this. So again, you kind of have your base functions here. A times e to the bx. Notice b is positive for growth, and then b is negative for decay. And then here's some of the graphs as well. So we've got our growth model. You can see the graph is increasing, decay, it is decreasing. Our Gaussian model, logarithmic or logistic growth model, natural logarithmic model, and common logarithmic model. So again, kind of wanted to just get those graphs in your brains so you have an idea of what the parent function looks like. Let's do a few more. Again, exponential growth and decay is a super kind of common, classic use for these types of functions. So we are going to practice them, and they do have quite a bit of applicable, uses in real life. So estimates of the world population in millions, of course, from 1995 through 2004 are shown in a table. An exponential growth model that approximates this data is the following. Come on. Okay, P equals 5344 e to the 0.012744 t. And again, we're going to be looking in between the years 5 and 14. So if this is my equation, and I want to find out when will the world reach 6.8 billion. So when will world reach 6.8 billion? Okay, so using this model, again, this is in millions. So this data is already in millions. So 6.8 billion in terms of million, that sounds kind of funny, is going to be 6,800. So we're going to use our equation, 5344 e to the 0.012744 t, and it's going to equal 6,800. So again, to start, I got to divide on both sides. It's glitching out on me. So I've got E. Why is this happening? 0.012744 t equals, this is approximately, let's say, call it 1.27246. 6,800 divided by 5,344. Now again, to get rid of e, I need to use the natural log. So ln and ln here, this is going to cancel out. 0.012744 t is approximately ln 1.27246. And then I need to divide 0.012744 divide by 0.012744. So plugging that into my calculator. All right, let's get a new line. So ln natural log of 1.27246 divided by 0.012744 gives me about 18.9. So again, that would be 18.9 years from when we started this graph. And so we started this, I forgot to mention that, but this data started in 1995. So 1995 plus 18 years, and that's going to give us 2008. that doesn't make sense. Never mind. Sorry about that. So again, to answer the question though, it would be 18.9. I misinterpreted the context of the problem, but again, it's more, the important part is understanding how to solve the problem. So let's do a couple more examples here. Let's try modeling population growth, one more of these. So in a research experiment, a population of fruit flies is increasing according to the law of exponential growth. After 2 days, there are 100 flies. After 4 days, there are 300 flies. How many flies will there be after 5 days? Okay, so that's our question. So how we go about this is, again, we know that our initial amount was 100 after 2 days, and then we had 300 after 4 days. So I can kind of put that into an equation. 100 equals, I don't know necessarily how many I started with, but my time was 2. And then I also knew that, hey, when I had 300 flies, I knew that my time was 4 days. So what we're going to do is we're going to solve for A in the first equation. So again, I'm going to think about, all right, I need to get A by itself. So that would be like saying 100 divided by E to the 2B equals A. And then when I am using my new equation, I can take this A value and plug it in right here. So 300 equals, instead of writing A, I'm going to write 100 over E to the 2B, and I still have E to the 4B on the outside. So I'm going to try to get rid of this. Again, so think about it in my denominator here. I have 100 E4B on top and E to the 2B on the bottom. So if you remember your exponent rules, okay, I can subtract these. So I'm left with 100 and then E to the 2B, because 4B minus 2B equals 2B. 2B or not 2B, that is the question. 300 equals 100 E to the 2B. We're going to divide by 100. We're going to divide by 100. And so that's going to cancel out. So we're going to be left with 3 equals E to the 2B. Now again, to get rid of E, I'm going to use the natural log. So I'm going to have ln 3, ln E to the 2B. That's going to cancel out. So ln of 3 equals 2B. Again, divide by 2, divide by 2. So I could say, or dividing by 2 is the same as multiplying by 1/2. But if I plugged into my calculator, okay, so let's say the natural log of 3 multiplied by 1/2 or multiplied by 2. I can get that number right there, but I'm actually going to keep it right there. So I'm going to say B equals 1/2 ln 3. And now I'm going to go back to my equation and I'm going to plug in this B value in for, instead of, what we did was we found the A value. Now I'm going to plug it in for B so that I can figure out what my time is going to be. Okay, so again, A equals 100 over E2, and then again, instead of writing B, I'm going to put my equation that I just found, 1/2 ln 3. And this is going to kind of simplify out because 2 times 1/2 cancels out. And now I'm left with 100 over e to the ln 3, but we know e to the natural log cancels out as well. So we're just left with a is equal to 100 over 3, which is approximately 33.33. So we can use this to create our model of y equals 33.33 e to the, again, we just found 1/2 ln of 3. We found to be 0.549. So we're going to put 0.5493 t in for B. T. And then my time, because the original question was how many fruit flies after 5 days. So I'm going to plug in a 5 for T, and I'm going to be able to get my answer. 33.33 E, 0.5493 times 5. And that's going to give me approximately 520 flies. A lot of work to get one example or one problem.